Tonight, we're going to attempt something that no human being has ever truly done. Not in a rocket, not in a spacecraft, not even in the imagination of most people who look up at the night sky. Tonight, we're going to try to cross the Milky Way. Not by flying through it, not by warping past its stars at impossible speeds, but by understanding it, by holding it in our minds, by feeling the true weight of what it would mean to go from one edge of our galaxy to the other. And I have to warn you now, before we take a single step. What you're about to discover is one of the most quietly terrifying things our species has ever had to reckon with. Here's something most people don't realize. When you look up at the night sky and see that faint pale smear of light stretching from horizon to horizon, that band of soft silver and shadow that ancient peoples called a river, a road, a river of milk spilled across the heavens, you're looking at a structure so vast that the human mind was never designed to hold it. The Milky Way is not simply big. It is 100,000 light-years across, 100,000 years of travel, even if you were moving at the speed of light itself, the fastest speed the universe allows, every single second of every single day, without ever slowing down, without ever stopping. 100,000 years, and you, tonight, are somewhere in the middle of it. By the end of tonight, you're going to understand exactly why crossing our own galaxy may be the most impossible journey ever conceived, and why the silence that surrounds that impossibility might be the most profound mystery in all of science. We're going to travel in our minds from where we are right now, tucked into a quiet spiral arm halfway between the center and the edge, all the way across this river of 400 billion suns, past the furnace at its heart, past the last scattered stars of its outer rim, and out into the darkness beyond, where our galaxy becomes just another smudge of light in an ocean of galaxies too numerous to count. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. There is a question that has been sitting quietly at the back of human consciousness for as long as we have known what the Milky Way actually is. It is not a complicated question. It does not require a degree in physics or a background in mathematics. You can ask it in 11 words, and most people, when they hear it for the first time as a real question, not a casual one, not a throwaway line, but a genuine, serious question, feel something shift inside them. Something opens up. Something gets just a little bit heavier. The question is this: how long would it take us to cross the Milky Way? Not to reach the nearest star. Not to travel to the edge of our solar system, which is itself a journey that took our fastest spacecraft nearly 4 decades. Not to visit another planet or loop around the moon. To cross the whole thing, from one side of our galaxy to the other. How long would that take? Tonight, that question is going to become the most interesting thing you have ever thought about. Most of us go through our entire lives without ever truly confronting what the Milky Way is. We hear the name, we use it casually, the way you might say the ocean or the mountains, as though it is simply a feature of the landscape, something enormous but familiar, something that belongs to the background of life rather than the foreground of our imagination. But the Milky Way is not a background feature. It is a structure of almost incomprehensible scale, a spinning disk of gas and dust and stars, 400 billion stars by the best estimates we have, arranged in sweeping spiral arms that reach outward from a blazing violent center into the relative quiet of the outer rim. And we live in it. We are inside it right now as you lie here, as your breathing slows, as the world outside goes dark and still. You are a passenger on a planet that orbits a star that is itself orbiting the center of a galaxy 100,000 light-years across. That is not a metaphor. That is the literal truth of where you are tonight. Now, 100,000 light-years. Let that phrase sit for a moment. It is easy to say. It rolls off the tongue without resistance, the way very large numbers often do. They sound impressive without quite landing, without quite making contact with the part of your brain that actually feels things. So let me try to make it land. A light-year is the distance that light travels in one full year. Light moves at approximately 186,000 miles per second. In a single second, a beam of light could circle the Earth 7.5 times. In 1 year, travelling at that speed without ever stopping, light covers nearly 6 trillion miles. 6 trillion miles is 1 light-year, The Milky Way is 100,000 of those. If you could somehow move at the speed of light, the fastest speed the universe permits, a speed so extreme that nothing with mass has ever achieved it, and you pointed yourself at the far edge of our galaxy and simply went, you would be travelling for 100,000 years before you arrived. 100,000 years at the speed of light. That is the galaxy you live in. Close your eyes for a moment and picture the Milky Way. Not the pale smear of light you might have seen on a clear night far from the city, though that is real, and we will come back to it. I mean the image you have seen in books, in documentaries, on the screens of phones and computers. The classic picture. A spiral. A flat glowing disk with long curving arms of light reaching outward from a bright central bulge, like a pinwheel caught mid-spin, like a slow whirlpool of stars frozen in a photograph taken from far above. That image is so familiar it has become almost mundane. Most people have seen it hundreds of times. And here is the thing most people don't realize. That image, as beautiful as it is, as accurate as it is in its basic shape, gives you almost no sense whatsoever of what the Milky Way actually is. It is like looking at a photograph of the Pacific Ocean taken from space and thinking you understand what it feels like to be in the water. The Milky Way is a barred spiral galaxy. That is its formal classification, and it matters more than it might sound. It is not a perfect pinwheel with smooth, graceful arms curving outward evenly in all directions. At its centre, there is not simply a bright hub of stars. There is a bar, a long rectangular structure of densely packed stars cutting across the galactic core from one side to the other, roughly 27,000 light-years in length. The spiral arms do not emerge from the centre itself, but from the ends of this bar, sweeping outward like the fins of some enormous cosmic creature turning slowly in the dark. This bar structure took us a long time to confirm, because confirming the shape of the galaxy you live inside is extraordinarily difficult. It is a bit like trying to draw a map of a city while standing in the middle of one of its busiest intersections, surrounded by buildings in every direction, with no way to rise above and look down. The disk of the Milky Way, the flat part, the part that contains most of the stars and gas and dust, is roughly 100,000 light-years in diameter. You have heard that number already, and you will hear it again, because it is the number that anchors everything we're going to explore tonight. But the disk is not uniformly flat. It has a thickness. In the region where we live, out in the quieter spiral arms, the disk is somewhere between 1,000 and 2,000 light-years thick. That sounds enormous, and it is. But compared to the width, it is remarkably thin. If you were to shrink the Milky Way down to the size of an ordinary dinner plate, the disk containing all of those stars would be roughly as thin as a sheet of paper. A sheet of paper 100,000 light-years across, with 400 billion suns embedded in it, slowly rotating around a common centre. That is the structure you call home. And then there is what lies beyond the disk. Because the Milky Way is not just its flat spinning disk of stars. Surrounding that disk, extending above and below it and out in every direction, is a vast and largely invisible structure called the galactic halo. The halo is a roughly spherical region, far less dense than the disk, populated by ancient stars and globular clusters and thin wisps of gas, that extends perhaps 100,000 light-years or more beyond the visible edge of the galaxy. Within this halo, and permeating the disk itself, is something we cannot see at all: dark matter. Dark matter is not a poetic name. It is a name born of ignorance, of the frank admission that we do not know what this substance is. We know it is there because of the gravitational effects it produces, the way the galaxy rotates, the way stars move, but it emits no light, reflects no light, interacts with nothing we can directly detect. The total mass of the dark matter halo surrounding the Milky Way dwarfs the mass of everything we can see. The stars, the gas, the dust, the planets, all of it together represents only a small fraction of the total mass of our galaxy. Most of what the Milky Way is made of is invisible to us. That is not a comfortable thought to sit with at night. Now, here is what I want you to hold in your mind as we move forward. The image of the Milky Way you know, that beautiful luminous spiral, is not wrong, but it is incomplete in ways that matter enormously for the journey we're imagining tonight. The galaxy is not an object you could look at from a distance and fully comprehend. It is not a thing the way a mountain is a thing, with edges you can walk around and a shape you can take in at a glance. It is a system a dynamic, churning, rotating system of almost incomprehensible complexity, governed by forces and filled with substances we're only beginning to understand. The stars you can see from Earth on the clearest night, every single one of them, every point of light in every direction, belongs to this one galaxy, and they represent only a tiny fraction of what is here. Most of the Milky Way's stars are invisible to the naked eye, hidden behind clouds of dust and gas, or simply too distant and too faint to register. We are surrounded by a universe we cannot see, inside a galaxy we cannot fully map, orbiting a star we take completely for granted. And tonight, we're going to try to cross it. Let me give you a number, and then I want to sit with you inside it for a while. 100,000 light-years. That is the diameter of the Milky Way, the distance from one edge of our galaxy to the other, measured across the widest point of the disk. We have said it already, more than once, and we will keep saying it tonight, because one of the strange properties of a number this large is that it requires repetition before it starts to feel real. It is like a word you have to say out loud many times before it stops sounding like nonsense and starts sounding like the thing it actually describes. 100,000 light-years. Say it slowly. Let it move through you, because I want to try to convert it into something your body can feel, not just your mind. A light-year, as we touched on earlier, is the distance light travels in 1 year. Light moves at approximately 186,000 miles per second. That is not a speed you can intuitively grasp. Nothing in ordinary human experience moves even close to that fast. But here is one way to feel it. The light reaching your eyes right now from the surface of the moon left the moon roughly 1¼ seconds ago. The light from the sun that warmed the Earth today left the sun about 8 minutes ago. The light from the nearest star beyond our sun, Proxima Centauri, just over 4 light-years away, left that star more than 4 years before it reached your eyes. When you look at Proxima Centauri in the night sky, you are not seeing it as it is tonight. You are seeing it as it was 4 years ago. And Proxima Centauri is our nearest neighbour. It is practically next door in galactic terms. The far edge of the Milky Way is 100,000 light-years away. The light arriving here from stars on that far rim departed before our species existed, before Homo sapiens walked the Earth, before the last ice age, before virtually everything we think of as human history had begun. Now let us convert this into miles, just to feel the full weight of it. 1 light-year is approximately 5.9 trillion miles. Written out, that is 5,900 billion miles for a single light-year. Multiply that by 100,000, and the diameter of the Milky Way comes to approximately 588 quadrillion miles. A quadrillion is 1,000,000 billions, 588 of them. There is no everyday object, no familiar frame of reference that helps you hold a number like that. Your brain was not built to feel the difference between a trillion and a quadrillion, the way it can feel the difference between a meter and a kilometer. These numbers exist at a scale where intuition simply gives up and walks away. And yet that distance is real. It is the actual size of the structure you live inside. The stars at the far edge of the galaxy are genuinely that far away, separated from you by that many miles of cold, dark, largely empty space. Here is another way to feel the silence of that distance. Imagine that the moment humans first mastered fire, roughly 1 million years ago, give or take, a radio signal was sent from Earth toward the far edge of the Milky Way. A simple signal, a pulse of electromagnetic radiation travelling outward at the speed of light, the way our television and radio broadcasts have been leaking into space for the past century or so. That signal, sent 1 million years ago, would today have travelled 1 million light-years. But the Milky Way is only 100,000 light-years across. So in this imagining, that ancient signal would have already crossed our entire galaxy, and then travelled 9 times that distance beyond it. It would be deep in the space between galaxies by now, 900,000 light-years past the far shore of the Milky Way, still going, still spreading outward in all directions, growing fainter with every passing year. And yet even that signal, travelling at the fastest speed the universe allows, started its journey 1 million years before any human alive today was born. This is the scale we're working with tonight. I want you to feel the silence too, not just the distance. When we talk about crossing the Milky Way, there is a tendency to picture something like a long road trip, a vast but ultimately traversable stretch of space, with stars scattered along the route like towns and rest stops, each one a potential destination, a place to refuel and take stock and continue onward. But that is not what crossing the galaxy would be like. The stars in the Milky Way are enormous in their own right, but they are separated by distances that make the space between them almost perfectly, absolutely empty. The average distance between stars in our region of the galaxy is roughly 4 to 5 light years. 4 to 5 years of travel at the speed of light, just to get from one star to the next nearest one. And most of those stars have no planets capable of supporting life, no warmth, no destination worth noting. The overwhelming majority of the crossing would be silence, darkness, nothing. The road between here and the far edge of the Milky Way is not a road lined with wonders at every turn. It is an ocean of emptiness, with islands of fire separated by distances so vast that the word lonely does not begin to cover it. That is the 100,000 light years of silence we're going to cross tonight. Before any journey can begin, you need to know where you are standing. You need a starting point, a fixed location on the map, a pin in the landscape, a place from which all distances and directions are measured. Tonight our starting point is a small, unremarkable yellow star located in the outer regions of a mid-sized spiral galaxy, approximately 26,000 light-years from the centre. That star is the Sun, and the planet orbiting it, the pale blue dot where every human being who has ever lived was born and died, is where you are right now. You're not at the centre of the galaxy. You're not near the edge. You're somewhere in the middle distance, tucked into a quieter region of one of the Milky Way's spiral arms, in a part of the galaxy that is, by cosmic standards, surprisingly calm and relatively uncrowded. That position, that particular address in the cosmos, is going to shape everything about the crossing we are imagining. The spiral arm we live in is called the Orion Arm, sometimes also referred to as the Orion Spur. It is not one of the Milky Way's major arms. The great sweeping primary arms of our galaxy, the Sagittarius Arm, the Perseus Arm, the Carina-Sagittarius Arm, are enormous, dense rivers of stars and gas and dust that curve outward from the ends of the central bar in long, graceful arcs. The Orion Arm is smaller. It is a partial arm, a spur, a branch extending outward between two of the major arms like a smaller tributary flowing away from a main river. It stretches for roughly 10,000 light-years in length, and our Sun sits somewhere near the inner edge of it, about halfway along its length. We are, in the grandest possible sense, living in the suburbs, not at the heart of things, not at the edge of everything, somewhere quiet and in between, which turns out to be an extraordinarily lucky place to be. Lucky because the galactic centre is not a pleasant neighbourhood. The closer you get to the core of the Milky Way, the more crowded and violent the environment becomes. Stars are packed together far more tightly near the centre, close enough in some regions that their gravitational fields interact, pulling and distorting each other's orbits in ways that would be catastrophic for any planet trying to maintain a stable, life-supporting path around its sun. Radiation levels near the core are ferocious, blasted outward by dense clusters of young, massive stars that burn hot and die young, exploding as supernovae and flooding the surrounding space with high-energy particles. And at the very centre of it all sits Sagittarius A star, this supermassive black hole that anchors the entire galaxy, with a mass equivalent to roughly 4 million of our suns, warping space-time around it in ways that make the physics of the region almost incomprehensible. We will spend more time there later tonight. For now, it is enough to know that our quiet address in the Orion Arm, 26,000 light-years from all of that, is not a coincidence to take lightly. From our position, the crossing we are attempting tonight runs outward in two possible directions. We could head inward, toward the galactic centre, through the increasingly dense and dangerous inner regions of the galaxy, past the blazing core and then out through the spiral arms on the far side. Or we could head outward, away from the centre, through the thinning outer disk, past the last scattered stars of the galactic rim, and into the halo. The total crossing, from the inner edge of the disk on one side to the outer edge on the other, is roughly 100,000 light-years, regardless of which route we take. But the two directions offer extraordinarily different journeys. Heading toward the centre means passing through fire, through radiation and density and gravitational violence. Heading toward the outer rim means passing through increasing emptiness, decreasing star density, and eventually arriving at a frontier where the galaxy simply fades, where the stars grow sparse and widely separated, and the darkness between them becomes the dominant feature of the landscape. Both routes are terrifying in their own way. Both illuminate something essential about what the Milky Way really is. There is something else worth noting about where we stand. Our sun is not stationary. Nothing in the galaxy is. Every star in the Milky Way is in motion, orbiting the galactic centre the way the planets of our solar system orbit the sun, but on a vastly larger scale and over vastly longer timescales. Our sun completes one full orbit of the Milky Way approximately every 225 million years. Astronomers call this the galactic year, or the cosmic year. In the roughly 4.5 billion years since the sun formed, it has completed only about 20 of these orbits. The last time our sun was in the same position in the galaxy that it occupies tonight, the dominant life forms on Earth were the earliest dinosaurs. The time before that, complex multicellular life had barely begun to emerge. We are slow travellers on a slow path around a slow centre, and the galaxy around us is also turning, also shifting, also evolving on timescales that dwarf anything our civilization has the ability to directly observe. This is where we begin. This quiet, turning 26,000 light-year removed from the centre of everything. This is our starting point. Now let us see how far we have to go. There is something quietly moving about the history of human speed. It begins so humbly, so slowly, so rooted in the physical limits of muscle and bone. For the vast majority of our existence as a species, for hundreds of thousands of years, the fastest any human being could travel was roughly the speed of a running body, perhaps 20 miles per hour at a full sprint, sustained for only seconds before exhaustion set in. For most of human history, long-distance travel meant walking. It meant the pace of a person carrying everything they owned on their back, covering perhaps 20 or 30 miles on a good day, stopping when darkness fell, sleeping on the ground, waking and walking again. The world was enormous at that speed. A journey of a few hundred miles could take weeks. The idea of crossing a continent was an undertaking measured in months. And the stars overhead, those cold, indifferent points of light, were simply decoration. Beautiful, navigational, mythological, but not destinations. Not yet. The acceleration of human speed across the centuries is one of the most dramatic arcs in our entire history. Domesticated horses extended our range and pace. Sailing ships let us cross oceans in weeks rather than the impossibility they once represented. The steam engine shattered the old limits entirely. Suddenly humans could move at 60, 70, 80 miles per hour without the biological cost of exertion, sustained over long distances carrying thousands of people and tons of cargo. The internal combustion engine pushed further. Aircraft pushed further still. By the middle of the 20th century, human beings had broken the sound barrier, moving faster than the speed of sound, roughly 760 miles per hour at sea level, something that would have been literally inconceivable to a person living just a few generations earlier. Each leap seemed to redefine what was possible. Each new speed made the previous limit look quaint, almost laughable. And then came the space age, and everything changed again. The first object built by human hands to achieve orbital velocity, the speed required to circle the Earth without falling back down, was Sputnik, launched by the Soviet Union in October of 1957. It travelled at roughly 17,500 miles per hour. That number, 17,500 miles per hour, was so far beyond anything humans had previously achieved that it barely seemed real. A few years later, astronauts aboard the Apollo missions travelled at speeds approaching 25,000 miles per hour during the return journey from the Moon, fast enough to cover the distance between New York and Los Angeles in roughly 6 minutes. These were extraordinary achievements, genuine leaps forward in what our species could do, and yet, measured against the scale of the galaxy, they were. And this is where the first chill of tonight's journey really sets in. Essentially nothing. Meaninglessly, heartbreakingly slow. The fastest object ever launched by human beings is Voyager 1. It was sent into space in September of 1977, nearly 50 years ago now, on a mission to study the outer planets of our solar system. It used a rare alignment of Jupiter, Saturn, Uranus and Neptune to perform a series of gravitational slingshot maneuvers, each one stealing a small fraction of the planet's orbital energy and adding it to Voyager's own speed. By the time it had completed those encounters and was heading out of the solar system entirely, Voyager 1 was travelling at approximately 38,000 miles per hour. 38,000 miles per hour. That is fast enough to circle the Earth more than once every second. It is fast enough to travel from Earth to the Moon in roughly 6.5 hours. It is the fastest any human-made object has ever travelled through space on a sustained, ongoing basis. And as of today, Voyager 1 is the most distant human-made object in existence, having crossed into interstellar space, the region beyond the influence of our Sun, making it the only thing we have ever built that has left the solar system entirely. So, here is the calculation, the one that I want you to feel in your chest rather than simply register in your mind. Voyager 1, the fastest thing we have ever built, is currently travelling at approximately 38,000 miles per hour. 1 light year, just one, is approximately 5.9 trillion miles. At Voyager's current speed, it would take roughly 17,500 years to travel a single light year. Not to cross the galaxy, not to reach the nearest star, to cover 1 light year. The nearest star to our Sun, Proxima Centauri, is 4.24 light years away. At Voyager's speed, reaching it would take approximately 73,000 years, and the far edge of the Milky Way is 100,000 light years away. At 38,000 miles per hour, the fastest speed any human civilization has ever achieved in space. Crossing our galaxy would take approximately 1.7 billion years. 1.7 billion years. The Earth itself is only 4.5 billion years old. Our entire planet has not existed long enough, from its moment of formation to right now tonight, to have completed even 3 crossings of the Milky Way at the speed of our fastest spacecraft. That is where we stand. That is what we have built, and that is the first, brutal, clarifying truth of the journey we are attempting. Sometimes the best way to understand a truly enormous number is to start with something small and familiar, and then scale it up slowly, step by step, until the weight of the thing finally lands. So let us do that tonight. Let us start with something you know. Let us start with a car. An ordinary car, the kind sitting in a driveway somewhere right now under the stars, cooling in the night air. Most cars on a highway travel at somewhere around 70 miles per hour. It is a comfortable speed, a human speed. At 70 miles per hour, you can cross a small country in a few hours, drive from one end of a large city to another in under an hour, cover 500 or 600 miles in a long day of driving. At 70 miles per hour, the world feels traversable. Distances feel conquerable. The road ahead feels like something that ends. Now let us take that car, that comfortable 70 miles per hour car, and point it at the edge of the Milky Way. Let us see what happens. At 70 miles per hour, driving without stopping, no rest, no sleep, no pauses of any kind, just continuous forward motion at highway speed. It would take you approximately 950 billion years to cross the Milky Way. 950 billion years. The current age of the universe is approximately 13.8 billion years. The universe has not been in existence long enough, not even close to long enough, for a car travelling at highway speed to complete this journey. If you had started driving at the moment the universe was born, in the first seconds after the Big Bang, you would today have covered less than 0.1% of the distance from one side of our galaxy to the other. The road ahead of you, even after 13.8 billion years of continuous driving, would be essentially unchanged. You would have barely left the driveway. That is 70 miles per hour. That is the speed of ordinary life. Let us try something faster. A commercial passenger aircraft travels at roughly 575 miles per hour, 8 times faster than the car. 8 times faster means the journey takes 8 times less time, which sounds encouraging until you do the arithmetic. At 575 miles per hour, crossing the Milky Way would take approximately 115 billion years, still more than 8 times the current age of the universe. You could fly from the moment of the Big Bang until today and cover only a small fraction of the crossing. The universe would have to grow 8 times older than it currently is before your plane reached the far edge of the galaxy. And here is something worth noting about that. The universe will not simply sit and wait. Stars are being born and dying while you fly. Galaxies are drifting apart. The cosmos is evolving, aging, changing in ways we're only beginning to model and understand. By the time a plane reached the far edge of the Milky Way, the universe it arrived in would be almost unrecognizable to the one it left. So let us try something much faster. Let us imagine a rocket, not the modest, slow-burning rockets of the early space age, but something genuinely capable. The Parker Solar Probe, launched in 2018 to study the Sun, is the fastest spacecraft ever built when measured at its closest approach to the Sun, where gravity accelerates it enormously. At its peak speed, the Parker Solar Probe travels at approximately 430,000 miles per hour. That is more than 11 times faster than Voyager 1. It is a speed that feels almost science fictional. 430,000 miles every single hour, day after day, year after year. At that speed, you could travel from Earth to the Moon in less than a minute. You could circle the Earth in under 4 seconds. Surely at 430,000 miles per hour, the galaxy starts to feel crossable. Surely the numbers finally become manageable. So let us check. At 430,000 miles per hour, crossing 100,000 light years, the full diameter of the Milky Way would take approximately 1.5 billion years. 1.5 billion years, even at the fastest speed any human object has ever achieved under the influence of gravity. The Earth would form, evolve life, watch the dinosaurs rise and fall, and still the crossing would not be complete. Speed that feels miraculous at a human scale remains absurdly, almost insultingly inadequate at galactic scale. And this is the lesson hiding inside all of these calculations. It is not simply that the galaxy is big, though it is. It is that our entire framework for thinking about speed and distance, the framework that feels perfectly adequate for navigating a planet, a solar system, even the inner reaches of space, collapses completely when confronted with galactic distances. The units break down, the intuitions fail, the sense of progress that comes with movement, the feeling that you are getting closer, that the destination is approaching, that feeling would simply not exist on a crossing of this scale. At any speed we have ever achieved, or are likely to achieve in the near future, the far edge of the Milky Way would not grow perceptibly closer in a human lifetime. It would not grow perceptibly closer in the lifetime of a civilization. The galaxy does not care about our rockets. It does not care about our fastest probes or our most ambitious engineering. It sits there, 100,000 light years across, patient and indifferent, and waits for us to find a better way. Tonight, we are going to look for one. Let us set aside rockets and cars and aircraft for a moment. Let us set aside every machine we have ever built and every speed we have ever achieved. Let us instead imagine something far more radical. Let us imagine that somehow, through engineering we do not yet possess, through physics we do not yet fully understand, we could travel at the speed of light itself, 186,000 miles per second, the fastest speed the universe permits, the absolute ceiling, the hard limit written into the laws of nature, the speed at which photons travel through the vacuum of space, and beyond which, as far as we currently understand, nothing can ever go. For decades, this has been the dream at the heart of science fiction. Warp drives, hyperdrive, the jump to light speed, the fantasy that if we could just reach that ultimate velocity, the galaxy would open up before us. Stars would become destinations. Other worlds would become reachable. The Milky Way would become something we could actually explore within a human lifetime. So let us check. Let us do the calculation that science fiction almost never does honestly. Let us find out what light speed actually buys us. At the speed of light, you would cross the diameter of the Earth in approximately 1/13 of a second. You would travel from the Earth to the Moon in 1.3 seconds. You would reach the Sun in 8 minutes and 20 seconds. You would pass the orbit of Neptune, the outermost planet of our solar system, in roughly 4 hours. In a single day of travel at light speed, you would cover approximately 16 billion miles. In a year, you would cover 1 light year, 5.9 trillion miles. These numbers feel vast, and they are. At the speed of light, the solar system becomes genuinely traversable in hours and days, rather than years and decades. Even the nearest star, Proxima Centauri, would be reachable in just over 4 years. For the first time in all of our calculations tonight, something begins to feel almost manageable, almost human. And then you point yourself at the far edge of the Milky Way, and you find the first cruel truth. At the speed of a light, the absolute maximum speed the universe allows, crossing the Milky Way takes 100,000 years. 100,000 years of continuous travel at 186,000 miles per second. No stops, no detours, no slowing down. 100,000 years. Let that settle into you for a moment, because this is the number that changes everything about how we think of our galaxy. We're not talking about the limits of our current technology anymore. We're not comparing ourselves unfavorably to some future, more advanced version of human engineering. We're talking about the speed of light itself, the theoretical ceiling, the fastest that any information or any object can ever travel. And even at that speed, our galaxy takes longer to cross than our species has existed. Homo sapiens have been on this planet for roughly 300,000 years. A lightspeed crossing of the Milky Way would take 1/3 of that entire span of human existence. It would span the rise and fall of civilizations so numerous and so distant from our own that we cannot even imagine them. Here is the thing most people don't realize about this number. It does not represent a failure of engineering. It does not represent a problem that more advanced technology will eventually solve. It represents something far more fundamental and far more unsettling. It represents the shape of the universe itself. The universe appears to be structured in such a way that even its own speed limit, even the fastest possible motion, is insufficient to make the Milky Way crossable on timescales that have any meaning for biological creatures like us. A human life lasts roughly 80 years. A civilization, if it is fortunate and careful and avoids the many ways civilizations can end, might last tens of thousands of years. Against the 100,000-year crossing time at light speed, even the longest-lived civilization we can plausibly imagine would be consumed entirely before the journey was complete. This is not a solvable engineering problem. This is the architecture of reality pressing against the smallness of life. And yet there is something even stranger buried inside this calculation. Something that took the genius of Albert Einstein to uncover, and that we will explore more fully in the chapters ahead. Lightspeed does something to time, something extraordinary, something that opens a small, strange window in the wall of impossibility we have just run into. When you travel at or near the speed of light, time does not pass for you the way it passes for everything you leave behind. The universe has a loophole, not in the speed limit itself, but in the way time behaves at the edges of that limit. It is a loophole so strange and so counterintuitive that most people, when they first encounter it, assume it must be wrong. It cannot really work like that. Time cannot really behave that way. But it does. The experiments have been done. The mathematics is airtight. Time is not the fixed universal constant we experience it to be in everyday life. It bends, it stretches, it slows, and at speeds approaching the speed of light, it slows in ways that could, in theory, make the impossible crossing feel like something else entirely to the traveller making it. That is where we're going next. But for now, sit with this. Even light, even the fastest thing in the universe, needs 100,000 years to cross the galaxy we call home. That is the first cruel truth of tonight's journey. And the night is still young. Let us slow down for a moment. Let us stop thinking about speed and time and calculations, and instead think about what the crossing would actually look like, what you would actually experience, what you would see outside the window of whatever vessel carried you across the 100,000 light-years of the Milky Way. Because there is a version of this journey that lives in the imagination, the science fiction version, the cinematic version, where crossing the galaxy means threading through a dense, glittering field of stars, passing close to blazing suns and colourful nebulae, navigating through clouds of luminous gas, always surrounded by the spectacular, always immersed in the visual richness of the cosmos. That version is not accurate, not even close. The reality of what lies between the stars of the Milky Way is something far quieter, far darker, and in its own way far more unsettling than any science fiction landscape. The reality is emptiness. Profound, absolute, almost unimaginable emptiness. The interstellar medium, the material that fills the space between stars, is not nothing, but it is closer to nothing than almost anything we can produce in a laboratory on Earth. It consists primarily of hydrogen and helium gas, with trace amounts of heavier elements and tiny solid particles called interstellar dust. But the density of this material is extraordinarily low. In the relatively dense regions of the interstellar medium, there might be 1 atom per cubic centimetre of space. 1 atom per cubic centimetre. The best vacuum chambers humans have ever built on Earth, rooms pumped down to the lowest pressures our engineering can achieve, contain millions of molecules per cubic centimetre. The space between stars is millions of times emptier than the emptiest thing we have ever created. If you were travelling through the interstellar medium, You would be moving through something that is, for all practical purposes, a perfect vacuum. There would be nothing to see, nothing to feel, nothing to indicate that you were moving at all except the slow, glacial shift of the stars themselves across the darkness ahead. And those stars, the destinations that might seem to line the road of a galactic crossing like lampposts along a highway, would offer no comfort of proximity. The average distance between stars in our region of the Milky Way is roughly 4 to 5 light years. 4 to 5 light years of travel at the speed of light just to move from one stellar system to the next. And remember, light speed takes 100,000 years to cross the full galaxy. So each individual step between neighbouring stars, 4 light years at light speed, would take 4 years. 4 years of travel just to reach a single neighbouring star, then another 4 or 5 years to the next, then another. The stars along this road are not close together. They are islands in an ocean of darkness, separated by distances so vast that the word neighbour loses most of its meaning. If our sun were the size of a basketball sitting in the middle of a large city, the nearest neighbouring star would be another basketball sitting in a city roughly 4,000 miles away. Along much of the crossing, you would also pass through regions where there are no stars at all, not because they do not exist somewhere in the galaxy, but because the distribution of stars across the Milky Way is uneven, and the spaces between the spiral arms are significantly emptier than the arms themselves. These interarm regions are stretches of the galaxy where star formation has been slower, where the density of luminous matter is lower, where the road between islands grows even longer and darker. Passing through an interarm region during our crossing would mean extended periods, thousands of light years potentially, where the nearest star in any direction was so remote that it would appear only as one more point of light against the background, indistinguishable from the rest. There would be no landmarks, no features, nothing to mark progress except the changing pattern of the stars ahead and behind, shifting so slowly that human perception, even on timescales of years, would struggle to register the movement. There is something else out in that darkness too, something that belongs to the interstellar medium, but that tells a more complex story about what the galaxy is made of and what moves through it. Rogue planets. These are worlds, some roughly Earth-sized, some much larger, that were ejected from their home solar systems billions of years ago by the gravitational chaos of planetary formation. They drift through the interstellar medium without any star to orbit, without any light to warm them, in temperatures close to absolute zero, completely dark, completely alone. Estimates suggest that the Milky Way may contain more rogue planets than it does stars, possibly many times more. They are almost entirely invisible to us. We have detected only a handful, and only because they passed in front of a background star and bent its light in a detectable way. But statistically, they are out there in the darkness between the stars, silent and frozen and uncountable. The road between stars is not entirely empty. It is populated by the lost and the dark and the forgotten. Cold worlds that will never know sunlight again, drifting through the silence between one light year and the next, witnesses to the crossing that never ends. If you chose to cross the Milky Way by heading inward, toward the centre rather than toward the outer rim, there would come a point in the journey where the darkness and emptiness of the interstellar road began to change. Gradually at first, then with increasing intensity, the star density around you would begin to rise. The islands of light that had been separated by 4 and 5 light years of void would begin to draw closer together. The background glow of the galaxy would deepen and brighten. Nebulae, vast clouds of gas and dust lit from within by the young stars being born inside them, would become more frequent, more dramatic, more colourful against the dark. And slowly, over thousands of light years of approach, you would begin to feel the presence of the galactic centre the way you might feel a city approaching at night long before you can see its skyline. As a glow on the horizon, a brightening of the sky, a growing sense that something enormous and powerful lies just ahead. The centre of the Milky Way is not a place of peace. It is one of the most violent environments in the known universe, and it is pulling at every star in the galaxy, including our Sun, with a gravity that has been shaping the structure of everything we call home for billions of years. At the heart of that centre sits Sagittarius A star. It is a supermassive black hole. Those two words, supermassive black hole, are used often enough in popular science that they can begin to lose their meaning, to slide past the mind without quite landing. So let me try to give them back their weight. Sagittarius A star has a mass equivalent to approximately 4 million of our suns. 4 million suns compressed into a region of space roughly the size of our solar system. Some estimates suggest the event horizon, the point of no return, has a diameter of roughly 15 million miles. For scale, that means the event horizon of the black hole at the centre of our galaxy is larger than the distance between the Earth and the Sun, an object so massive that not even light can escape from within it, that warps the space-time around it into configurations that break our everyday intuitions about how the universe works, sitting at the centre of the galaxy we live in, 26,000 light-years away, quietly anchoring the rotation of 400 billion stars. It has been there for billions of years. It will be there long after our sun has burned out and gone cold. And Sagittarius A star is not alone in its violence. The region surrounding the galactic centre, a zone roughly 1,000 light-years across called the Central Molecular Zone, is one of the most extreme environments in the Milky Way. It is filled with dense clouds of molecular gas, with young star clusters packed together at densities hundreds of times higher than in our quiet neighbourhood. Stars in the Central Molecular Zone are born faster, burn hotter, and die more dramatically than stars in the outer regions of the galaxy. Massive stars 10, 20, 50 times the mass of our Sun, form here in large numbers, blaze through their short lives in millions rather than billions of years, and end in supernovae that blast enormous quantities of energy and material outward into the surrounding medium. The radiation environment near the galactic centre is ferocious. X-rays, gamma rays, cosmic rays, forms of high-energy radiation that would be lethal to unprotected biological life, permeate the region at levels far beyond anything experienced in the calm outer disk where our solar system resides. In 2022, astronomers using the Event Horizon Telescope, a global network of radio observatories linked together to function as a single Earth-sized telescope, captured the first direct image of Sagittarius A star itself. It was a historic moment. For the first time, humanity had a direct visual record of the object at the centre of our own galaxy, a dim, glowing ring of superheated material swirling around a dark central shadow, the silhouette of the event horizon itself. The image was blurry by everyday standards, but the achievement it represented was staggering. We had photographed the heart of the Milky Way. We had seen the darkness at the centre of our home, and what struck many people who looked at that image was not its clarity but its strangeness. The sense that this object, this ancient and incomprehensible thing, had been there all along, hidden behind the dust clouds of the galactic plane, while everything we have ever known and loved orbited it at a respectful and fortunate distance. For any crossing of the Milky Way that passed through the galactic centre, this region would represent the most dangerous and most spectacular portion of the entire journey. The crowding of stars, the radiation, the gravitational complexity of orbits near a supermassive black hole, all of it would make the Central Molecular Zone a gauntlet rather than a road. Passing through it would require shielding against radiation levels that dwarf anything encountered in the outer galaxy. It would mean navigating through a region where stars are close enough that their gravitational influences overlap and interfere, where the risk of encounter with stellar remnants, neutron stars, stellar mass black holes, white dwarfs, is orders of magnitude higher than in the quiet Orion arm we call home. And at the centre of it all, Sagittarius A star would sit in the darkness ahead, not glowing in any ordinary sense, but detectable by the disk of superheated material spiralling into it, by the gravitational lensing of stars behind it, by the distortion it imprints on the very fabric of space. To pass close to it and survive, if survival were possible, and then to emerge on the other side into the quieting starfields of the far inner arm, would be to have crossed through the most extraordinary and terrifying landmark in the entire galaxy. The galactic centre is not a destination, it is a test, and the road through it is paved with fire. There is a thought experiment that has lived at the edges of human imagination for nearly a century now. It surfaces in science fiction, in serious academic papers, in the quiet late-night conversations of people who have looked up at the stars long enough to ask the uncomfortable question, if we cannot travel fast enough to cross the galaxy in a single lifetime, what if we simply built a ship large enough and sturdy enough to carry not just one generation of travellers, but many? What if the ship itself became the world? A self-contained civilization, a closed ecosystem of air and water and food and community, launched toward a distant destination with the understanding that the people who boarded it would never arrive, that their children would never arrive, that perhaps their grandchildren's grandchildren's grandchildren would be the ones to finally step out onto whatever waited at the journey's end. This is the concept of the generation ship, and the more carefully you think about it, the more it reveals something profound and quietly heartbreaking about what it means to be a living creature trying to exist at the scale of the galaxy. The engineering challenges of a generation ship are staggering, but, in principle, not impossible. You would need a vessel large enough to house a viable population. Geneticists generally estimate that a minimum of several hundred individuals, and ideally several thousand, would be required to maintain sufficient genetic diversity over the centuries or millennia of travel to avoid the health consequences of inbreeding. You would need closed-loop life support systems capable of recycling air, water and nutrients indefinitely, with redundancy upon redundancy to survive the inevitable failures of components over timescales of centuries. You would need energy sources, perhaps nuclear fission or fusion reactors, capable of powering the ship and its systems for the entire duration of the crossing. You would need shielding against cosmic radiation, which over the timescales involved would otherwise cause devastating damage to the health of the passengers. And you would need a social structure, laws, governance, education, culture, memory, capable of holding a human community together across generations so numerous that the original destination might begin to feel like mythology rather than goal. But the engineering, as daunting as it is, may not be the hardest problem. The hardest problem may be the human one. Think about what it would mean to be born on a generation ship, to grow up in a vessel whose walls define the entire physical extent of your world, to know from childhood that you will live your entire life, every joy, every loss, every relationship, every ordinary Tuesday, inside this ship, moving through the darkness between stars, and that you will die inside it without ever having set foot on a planet, without ever having felt real gravity or real wind or real sunlight on your skin. You did not choose this life. You were born into it, the way people are born into circumstances they did not select and cannot escape. Your parents were born into it. Perhaps their parents were born into it. The world you inhabit is the same world they inhabited. The same corridors and hydroponic gardens and observation decks. The same recycled air and artificial light. The same stars slowly shifting in the viewports over the decades and centuries of travel. What would that do to a person? What would it do to a culture? There is a term that philosophers and ethicists who study this question have developed. The non-identity problem is applied to generation ships. The people born and living and dying in the middle generations of such a voyage, the ones who will never see the origin and will never see the destination, did not consent to their situation. They exist only because the voyage began. They could not have existed otherwise, and yet they are asked to dedicate their entire lives to a project whose completion they will never witness, serving as living links in a chain stretching from a world they have never known to a world they will never reach. There is something both noble and troubling about this. Noble because it represents a commitment to something larger than any individual life, a gift given forward to descendants not yet born. Troubling because it asks the middle generations to find meaning in a journey they are, in a very real sense, simply passing through. And here is what makes the generation ship concept most relevant to our crossing tonight. Even a generation ship, even the most optimistic, most generously engineered, most socially cohesive generation ship we can imagine, would not solve the timescale problem of crossing the Milky Way at speeds achievable with any foreseeable propulsion technology. At the speed of our fastest current spacecraft, the crossing would take 1.7 billion years. No generation ship could survive for 1.7 billion years. No social structure, no engineering, no material known to science could maintain coherence across that span of time. Even at speeds 100 times faster than Voyager 1, speeds we have no current means of achieving, the crossing would take millions of years, thousands of generations. The gap between where we are and where we would need to be, technologically, to make a generation ship crossing of the galaxy, even theoretically viable, is itself a chasm almost as daunting as the crossing. The generation ship is not a solution to the problem of crossing the Milky Way. It is a meditation on the problem. It is a way of making the timescale feel human, of translating the incomprehensible into the merely heartbreaking. And in that translation, it tells us something true and important, that the galaxy is not simply distant. It is distant in a way that reaches into the deepest questions about what life is for, what we owe to the generations that come after us, and whether there are journeys worth beginning even when we know we will never see them end. In 1905, a 26-year-old patent clerk in Bern, Switzerland, published a paper that quietly dismantled everything humanity thought it understood about the nature of time. His name was Albert Einstein, and the paper was his special theory of relativity. It did not arrive with fanfare. It did not immediately transform the world. But what it contained was one of the most shocking and most consequential ideas in the history of human thought, that time is not fixed, not universal, not the same for everyone. Time, Einstein showed, is a dimension, like the 3 dimensions of space, and it behaves differently depending on how fast you're moving through it. The faster you move, the slower time passes for you relative to someone who is standing still. This is not a metaphor. It is not a philosophical abstraction. It is a measurable, verifiable, experimentally confirmed property of the universe we live in. And for the crossing of the Milky Way, it opens a door that everything else we have discussed tonight has kept firmly shut. The effect Einstein described is called time dilation. At the speeds of ordinary life, walking, driving, even flying in a jet aircraft, the effect is so vanishingly small that it is completely undetectable without extraordinarily precise instruments. But it is there. Atomic clocks flown on aircraft tick very slightly slower than identical clocks left on the ground. GPS satellites, which move at roughly 8,700 miles per hour in orbit, must have their clocks corrected for time dilation, or the navigation errors would accumulate to the point of making the system useless within a single day. These are real corrections, applied in real engineering, accounting for a real physical phenomenon that Einstein predicted from pure mathematics more than a century ago. Time dilation is not theoretical speculation. It is operational fact, embedded in the technology billions of people use every day without knowing it. Now here is where it becomes relevant to our crossing. The closer you get to the speed of light, the more dramatic the time dilation effect becomes. It does not scale linearly. It accelerates, growing more and more extreme as you approach the ultimate speed limit. At 10% of the speed of light, the effect is small but measurable. At 50%, it is more noticeable. At 90% of the speed of light, time for the traveller passes at roughly 44% of the rate it passes for someone standing still. At 99% of light speed, time for the traveller passes at roughly 14% of the rate experienced by a stationary observer. And as you push closer and closer to 100%, as you approach but never quite reach the speed of light itself, the time dilation factor grows toward infinity. Time for the traveller slows more and more, approaching but never quite reaching a complete stop. This is the loophole. Not in the speed limit, you still cannot exceed the speed of light, but in time itself. Let us apply this to the crossing. Imagine a spacecraft that could somehow accelerate to 99.9999% of the speed of light, an almost incomprehensibly difficult engineering achievement, but one that does not violate any known law of physics. At that speed, the time dilation factor would be enormous. For every year that passed aboard the ship, thousands of years would pass in the outside universe. The crossing of the Milky Way, 100,000 light years, would still take 100,000 years as measured from Earth, from the outside, from the perspective of anyone watching the ship depart and waiting for it to arrive. But for the travellers aboard the ship, subjective time would pass far more slowly. Depending on the exact speed achieved, the crossing could feel, to the people making it, like decades rather than millennia. A traveller aboard such a ship, launched toward the far edge of the galaxy, could theoretically arrive within a single human lifetime as experienced on the ship, while 100,000 years elapsed in the universe outside. They would step off the ship onto the far shore of the Milky Way having aged perhaps 60 or 70 years, and the galaxy they had left behind would be 100,000 years older than the one they remembered. This is where the loophole opens into something both wondrous and deeply, quietly terrifying. Because the time dilation that compresses the journey for the traveller does nothing to compress it for everything else. Earth would be 100,000 years older. The sun would have burned through another 100,000 years of its hydrogen fuel. Every person the traveller had ever known, every friend, every family member, every thread of connection to the life they left behind, would be gone. Not just dead, but incomprehensibly ancient history, separated from the moment of departure by a gulf of time larger than the entire recorded history of human civilization multiplied many times over. The traveller would arrive at the far edge of the Milky Way as a living person in a recognizable body, carrying memories of a world that no longer existed in any meaningful sense. They would have crossed the galaxy, and they would be utterly, cosmically, irreversibly alone. Time dilation is the loophole in the laws of physics that makes the crossing theoretically survivable for an individual human being. But the price it extracts is everything. It is the universe's way of reminding you that there are no free crossings. There is no journey without cost. The galaxy will let you cross it, but it will take everything you ever loved in exchange. There is a question that tends to get skipped over in conversations about near light speed travel. It gets skipped because the answer is so extreme, so far beyond the boundaries of anything we can currently produce or even meaningfully plan for, that engaging with it seriously can feel almost absurd. But tonight we're engaging with everything seriously, so let us ask it. How much energy would it actually take to accelerate a spacecraft to the speeds we discussed in the last chapter, to 99% or 99.99% of the speed of light? How much energy does the time dilation loophole actually cost? Because the universe does not give that loophole away for free. Einstein's equations are generous in what they permit, but they are ruthless in what they demand in return. And what they demand, in the case of near light speed travel, is energy on a scale that reframes the word impossible in ways that feel almost personal. Let us start with a number from the world we actually inhabit. The total energy consumed by all of human civilization in a single year, every power plant, every vehicle, every device, every light and screen and factory and heater on the entire planet, is approximately 5.8 times 10 to the power of 20 joules. That is a large number, but it is a number that represents something real and tangible, the total energetic output of our species, our entire technological civilization, over 12 months. Now let us think about what it would take to accelerate even a modest spacecraft, say a vessel massing around 1,000 tons, roughly the weight of a small naval destroyer, to 99% of the speed of light. The kinetic energy required, calculated using the relativistic equations Einstein gave us, comes to approximately 9 times 10 to the power of 23 joules. That is roughly 150 times the total annual energy consumption of all human civilization. 150 years of our planet's entire energy output poured into accelerating a single ship to 99% of light speed. And we have not yet mentioned slowing it down at the other end, which requires the same amount again. Push the speed higher, toward the 99.9999%, that would make the time dilation truly dramatic. That would compress a 100,000 light-year crossing into a human lifetime. And the energy requirements do not simply rise proportionally, they skyrocket. The relativistic equations are nonlinear near the speed of light, meaning that each additional fraction of a percent of light speed costs vastly more energy than the fraction before it. Getting from 99% to 99.9% requires more additional energy than getting from 0 to 99% in the first place. Getting from 99.9 to 99.99 requires more again. The energy curve bends upward toward infinity as you approach the speed limit, which is precisely why the speed limit holds. Not because of some arbitrary rule, but because reaching it would require literally infinite energy, and infinite energy does not exist. The universe enforces its speed limit not with a wall, but with an ever-steepening hill that no finite amount of fuel can ever fully climb. There is another layer to this problem that rarely gets discussed. Even if you had the energy, even if some future civilization had access to power sources we cannot currently conceive of, capable of delivering the required joules, there is the question of what you do with that energy during the crossing itself. A spacecraft travelling at a significant fraction of the speed of light is not travelling through empty space in any safe sense. The interstellar medium, those sparse atoms of hydrogen and helium we described earlier, less than 1 particle per cubic centimetre, becomes a problem at near light speed. At those velocities, each hydrogen atom the spacecraft encounters hits the hull with the energy of a cosmic ray. The cumulative radiation dose from billions upon billions of such impacts over a crossing of any significant distance would be lethal without extraordinarily massive and heavy shielding. But adding shielding adds mass. Adding mass increases the energy required to accelerate the ship. Increasing the energy required increases the fuel needed. Increasing the fuel needed increases the mass further. This is a feedback loop, a compounding spiral of requirements that makes the engineering challenge not just difficult, but potentially self-defeating. Every solution creates a new problem. Every answer opens a new question. And yet there are serious scientists and serious engineers who have not given up on this problem. Not because they think it is easy, not because they believe a solution is imminent, but because the history of human technology is, in one reading, a history of impossible things becoming possible over timescales longer than any single generation could imagine. Nuclear power was inconceivable to a person living in the 18th century. Quantum computing would have been meaningless to the engineers who built the first steam engines. The gap between what we can do today and what near light speed travel would require is enormous. But it is a gap measured in engineering and energy and time, not a gap that requires any new physics. The laws of the universe as we currently understand them permit it. They make it extraordinarily difficult and extraordinarily costly, but they do not forbid it. And there is something in that fact, something small but persistent, like a light at the end of a very long tunnel, that keeps the question alive. The energy problem is real. The cost is staggering. But the universe has left the door unlocked. It has simply put it at the end of a road so long that we have not yet been able to see where it leads. The Milky Way is approximately 13.6 billion years old. Our solar system, by contrast, is 4.6 billion years old. That means there was a window of roughly 9 billion years, during which stars were forming, planets were coalescing, and the conditions for life were potentially emerging in our galaxy before our sun had even ignited. 9 billion years is a number so large it dissolves meaning on contact. But try to hold it for a moment, because it matters enormously for the question we're about to ask. If complex life can arise on a planet within roughly 4 billion years of that planet's formation, which is what happened on Earth, then there could theoretically have been civilizations in the Milky Way that arose 4 or 5 billion years before our own. Civilizations that had not thousands of years of technological development, not tens of thousands, but billions of years of potential advancement ahead of us before the first human ancestor ever stood upright on the African savanna. Civilizations that may have had time, more than enough time, to solve every engineering problem we have discussed tonight, to cross the galaxy not once but many times. So where are they? Why is the Milky Way so quiet? Why, when we look up at the sky with every instrument we have, do we find no radio transmissions, no signs of engineering, no evidence of the vast civilizations that 9 billion years of head start should have produced? This is the Fermi paradox, and it may be the most terrifying question in all of science. The physicist Enrico Fermi first articulated the paradox in its most direct form in a casual lunchtime conversation in 1950, when he reportedly looked up from his meal and asked his colleagues a simple question: where is everybody? The logic behind the question is airtight and has resisted every simple resolution for more than 7 decades. The galaxy is old. Life arose quickly on Earth, suggesting it may not be extraordinarily rare. Even at the modest speeds of our current technology, a sufficiently motivated civilization could colonize the entire Milky Way, every star system, every potentially habitable world, within a few tens of millions of years, through a process of self-replicating probes or slow generational expansion. A few tens of millions of years is a long time to a human, but it's less than 1% of the age of the galaxy. Any civilization that arose even 1% earlier than us and chose to expand should have colonized the entire galaxy before our sun was born. The numbers say the galaxy should be full, and yet we find nothing, no signals, no megastructures, no visitors, complete silence. The proposed solutions to the Fermi paradox are numerous and range from the comforting to the deeply unsettling. Perhaps life is simply rarer than we hope, rare enough that we are genuinely among the first intelligent species to arise in the Milky Way, or even in the observable universe. This is the rare Earth hypothesis, and it offers a kind of strange comfort. We are not being ignored or avoided, we are simply early, pioneers in a galaxy that is not yet filled with voices. Perhaps civilizations routinely arise but routinely destroy themselves before they develop the technology for galactic expansion, through war, through environmental collapse, through the misuse of technologies whose power outstrips the wisdom required to control them. This explanation has a particular resonance when you look at our own trajectory as a species. Perhaps communication across galactic distances is simply harder than we assume, and the signals are out there but encoded in forms or frequencies or methods we have not yet thought to look for. Perhaps other civilizations are listening too, all of them waiting, all of them silent, all of them hoping someone else will speak first. But there is one proposed solution to the Fermi paradox that I find myself returning to on nights like this one. It is called the dark forest hypothesis. It suggests that the silence of the cosmos is not accidental and not the result of absence. It suggests that intelligent civilizations do exist, many of them perhaps, but that they have learned, through whatever tragic experience their history required, that broadcasting your existence in a universe of unknown and potentially hostile actors is extraordinarily dangerous. In this model, the galaxy is not empty. It is full of civilizations hiding, listening but not speaking, watching but not waving. Each one aware that the resources of the universe are finite, that any sufficiently advanced civilization represents a potential existential threat to any other, and that the safest strategy in a cosmos you cannot fully understand is to make yourself as invisible as possible. In the dark forest, every light is a target. In the dark forest, silence is survival. If this hypothesis is correct, then our radio transmissions, leaking outward from Earth for the past century at the speed of light, now forming a bubble 100 light-years across centered on our sun, may be the most dangerous thing our civilization has ever done. What does any of this have to do with crossing the Milky Way? Everything. Because if the crossing is theoretically achievable, if time dilation and sufficient energy make it survivable, and if the galaxy has been old enough for long enough that other civilizations should have done it, then the silence that greets us when we look at the sky is not just a scientific mystery. It is a data point, a clue, a piece of evidence about the nature of the universe that has not yet yielded its full meaning. Either we are alone in a galaxy vast and ancient and empty of other minds, which is terrifying in one way, or we're not alone, and something about the crossing, something about the attempt, something about the reach itself has prevented every civilization before us from completing it, or from wanting to announce that they did, which is terrifying in an entirely different way. The silence of the Milky Way is not peaceful. It is the silence of an enormous, dark, ancient room that you cannot see across, in which you cannot tell whether you are the only one present, or simply the only one making noise. Imagine for a moment that you have made it. Imagine that somehow, through engineering we do not yet possess, through energy sources we have not yet discovered, through courage and patience and sacrifice that dwarfs anything in the history of our species, you have crossed the 100,000 light years. You have passed through the quiet darkness of the interstellar medium, through the crowded and violent inner regions of the galaxy, and out through the far spiral arms on the other side. The journey is behind you. The destination, whatever that means after such a crossing, is here. You're at the edge of the Milky Way, and what you find when you arrive is not what you might have expected. It is not a wall, not a boundary marker, not a dramatic cliff edge where the stars end and the void begins. The edge of the galaxy is something far more subtle, far more gradual, and in its own quiet way, far more haunting than any sharp border could be. The outer disk of the Milky Way does not end cleanly. It fades. The spiral arms, which in the inner galaxy are dense and luminous and structurally distinct, become ragged and sparse as they extend outward. Stars grow further apart. The gas and dust that feed star formation thin out. New stars become rarer, older stars more dominant. Ancient red dwarfs and dim orange suns that have been burning quietly for billions of years, outlasting the more spectacular but shorter-lived massive stars of the inner galaxy. The character of the region changes from dynamic to serene, from the busy middle of a city to the quiet outskirts, where the houses are far apart and the nights are genuinely dark. Eventually, at distances of roughly 60,000 light-years from the galactic centre, on the far side from us, given that we sit about 26,000 light-years from the centre, the disk thins to the point where calling it a disk becomes a generous description. Beyond that, stars still exist, but they are scattered, isolated, separated by distances even greater than the 4 or 5 light-years typical of our own neighbourhood. They are the last outposts, the frontier. Beyond the outer disk, the galactic halo takes over. The halo is ancient. It is made predominantly of the oldest stars in the Milky Way, stars that formed in the earliest epochs of the galaxy's history, more than 12 billion years ago when the universe itself was young and the Milky Way was still assembling itself from the primordial clouds of gas that formed after the Big Bang. These halo stars are poor in what astronomers call metals, which in astronomical parlance means any element heavier than hydrogen and helium. They formed before generations of stellar explosions had seeded the galaxy with the heavier elements that make planets and chemistry and ultimately life possible. They are relics, fossils of the early universe, orbiting the galaxy in long, looping paths that take them far above and below the plane of the disk. Standing at the far edge of the Milky Way and looking outward through the halo, you would see these ancient stars scattered sparsely in every direction. Dim, old, and patient, burning with a fraction of the energy of the young stars at the galaxy's heart. And then, beyond even the halo, you would see something that no human eye has ever seen from inside: the Milky Way's satellite galaxies. The large and small Magellanic Clouds, visible from Earth's southern hemisphere as detached patches of the Milky Way bright enough to see with the naked eye on a clear night, are dwarf galaxies gravitationally bound to our own, orbiting the Milky Way the way moons orbit a planet. From the far shore of our galaxy, they would appear as separate, distinct islands of light in the darkness beyond. The large Magellanic Cloud, perhaps 160,000 light-years away, glowing with the light of its own billions of stars, close enough in galactic terms to feel like a neighbour, but far enough to remind you that you have now reached the edge of home. Beyond the Magellanic Clouds, further still, the great spiral of Andromeda would hang in the darkness. 2.5 million light-years away, the nearest large galaxy to our own, visible as an elongated smear of pale light, the most distant object the human eye can see without a telescope. From the far shore of the Milky Way, Andromeda would appear no differently than it does from Earth. 2.5 million light-years does not compress meaningfully at the scale of a 100,000 light-year crossing. There is one more thing waiting at the galaxy's edge that I want you to hold in your mind as we prepare to turn and look back. The intergalactic void. Beyond the last scattered stars of the halo, beyond the satellite galaxies, beyond everything that belongs in any meaningful sense to the Milky Way, lies a darkness of an entirely different quality from the interstellar darkness we have travelled through. The space between galaxies is not merely empty in the way the space between stars is empty. It is emptier. The interstellar medium, sparse as it is, contains at least a few atoms per cubic metre. The faint residue of stellar winds and supernova ejecta, and the slow diffusion of gas across the galaxy over billions of years. The intergalactic medium is so thin that the word vacuum barely covers it. Vast regions of intergalactic space contain fewer than one atom per cubic metre. In these voids between the galaxy clusters, the cosmic web of filaments and sheets and empty bubbles that defines the large-scale structure of the universe, almost nothing exists. Not stars, not gas, not dust, not even much dark matter. Just space, expanding, carrying the galaxies apart from each other at speeds that grow with distance, until the most remote galaxies are receding faster than light can ever bridge the gap. You have reached the edge of the Milky Way. Behind you lies everything that has ever mattered to our species. Ahead lies the intergalactic night, and it is very, very dark out there. Turn around. You have crossed 100,000 light-years. You're standing in this imagining at the far edge of the Milky Way, at the ragged outer frontier where the last scattered stars of the galactic halo thin into the intergalactic void. The crossing is behind you, and now for the first time you turn and look back at what you have left. What you see is the galaxy, the whole thing, from the outside, or rather from just outside. Close enough that it fills a significant portion of the sky, close enough that structure is visible, close enough that you can see the faint spiral arms curving outward from the central bar, the glow of the core, the dimmer outer disk fading into the darkness at the edges. It is beautiful. It is one of the most beautiful things that has ever existed, anywhere, in the history of the universe. A slowly rotating disk of 400 billion suns, 100,000 light-years across, burning with the combined light of everything our species has ever called home. And somewhere inside it, buried in the glow of one of those outer spiral arms, is a single ordinary star. And orbiting that star, invisible at this distance, lost in the light of hundreds of billions of neighbours, is a small blue planet. And on that planet right now, billions of people are living their lives, sleeping, breathing, dreaming, completely unaware that they are being thought of from 100,000 light years away. Here is what I want you to feel in this moment. Not the grandeur of the view, though it is grand beyond any scale our imagination comfortably handles. I want you to feel the invisibility. The Earth, from the far edge of the Milky Way, is not merely small. It is not merely a dot or a point of light, the way it appears in photographs taken from the outer solar system. From 100,000 light years away, the Earth does not exist as a visible object at all. The Sun, with its light, is itself one dim star among hundreds of billions, too faint, too small, too ordinary to distinguish from the background glow of the galaxy without instruments of almost incomprehensible precision. Everything that has ever happened on Earth, every war, every discovery, every empire, every love story, every piece of music ever composed and heard, every meal ever shared between people who cared about each other, all of it is buried inside that faint, undifferentiated light, indistinguishable from the billions of other stars surrounding it. You cannot point to it. You cannot find it. Earth, from this distance, is not even a pale blue dot. It is a pale idea. And now consider the light you're seeing. The light reaching your eyes from the centre of the galaxy, from the far side of that luminous disk, left its source 50,000 years ago, when our ancestors were living in small bands, painting the walls of caves, navigating by the same stars that still burn overhead tonight. The light from our own spiral arm, from the region near our Sun, is 26,000 years old by the time it reaches this vantage point. If you could somehow pick out the light of our Sun specifically from this distance, you would be seeing it as it was 26,000 years ago, before the invention of writing, before the rise of the first cities, before agriculture, before almost everything we associate with the word civilization. The Sun you would be seeing from here has not yet warmed a single human settlement. The Earth orbiting it has not yet seen a single field planted or a single city built. You would be looking at our star in its pre-human epoch, shining with complete indifference over a planet that has not yet been given a name. This is the thing about cosmic distance that cuts deepest, I think. It is not just that the universe is large, though it is. It is that the universe is old and large simultaneously, and these two properties combine to produce something almost unbearable in its implications. We can never truly see the cosmos as it is right now. We can only ever see it as it was. Every photon that reaches our eyes, from any source beyond our immediate surroundings, is a message from the past. The more distant the source, the older the message. From the far edge of the Milky Way looking back, we would not be seeing our galaxy as it is tonight. We would be seeing it as it was 100,000 years ago, before our species had spread across the Earth, before the last ice age had ended, before the first humans had crossed into the Americas or the Pacific. The galaxy we would be seeing is an ancient photograph, a record of a time when we did not yet exist as the civilization we have become, and the galaxy right now, tonight, as it actually is in this moment. We will never see that from that distance. By the time any light from this moment reaches that far shore, 100,000 years will have passed. Whatever we are now, in this moment, will be as remote to whoever or whatever looks back then as the cave painters of southern Europe are to us. I find this thought strangely, not only humbling, but also quietly comforting. There is something in it that softens the weight of ordinary human anxieties, the things that feel so urgent in a single life, the pressures and worries and disappointments that crowd in on a tired Tuesday night, do not disappear when held against the scale of 100,000 light years, but they change shape. They become part of something so much larger that the change in perspective itself feels like a kind of relief. You are on a planet that cannot be seen from the edge of the galaxy you live in. You are a temporary arrangement of atoms on a world that is invisible from within its own home. And yet you are here, thinking, feeling, looking up at a sky full of light that left its sources before you were born, before your civilization was born, before your species was born. You are the universe's way of looking back at itself across distances it took 100,000 years to cross. That is not nothing. That is in fact almost everything. Here is something I want you to know before you close your eyes tonight. Something that is true right now, in this moment, as you lie still and breathe slowly and let the weight of the cosmos settle gently around you. You're not stationary. You have not been stationary for a single second of your life. The stillness you feel, the quiet of the room, the motionlessness of your body, the sense that you are resting while the universe moves around you, is an illusion produced by the comfortable scale of human experience. At the scale of the galaxy, at the scale of the journey we have been taking together tonight, you are already in motion. You have always been in motion, and the speed at which you are travelling right now, without effort, without engines, without any technology at all, would have seemed absolutely impossible to every human being who ever lived before the age of modern astronomy. You're not standing still, you're hurtling through space at a speed that dwarfs anything our fastest spacecraft have ever achieved. You just cannot feel it. And that, in its own quiet way, is one of the most extraordinary things about being alive on this particular planet, in this particular galaxy, at this particular moment in the history of the universe. Let me give you the numbers because they deserve to be felt. The Earth rotates on its axis, carrying you, depending on your latitude, at somewhere between 0 and roughly 1,040 miles per hour relative to the Earth's centre. The Earth orbits the Sun at approximately 67,000 miles per hour. The entire solar system, the Sun and all its planets, including the Earth, including you, orbits the centre of the Milky Way at approximately 515,000 miles per hour. 515,000 miles per hour. That is roughly 140 miles every single second, sustained continuously, day after day, year after year, for as long as the galaxy has existed. And on top of all of that, the Milky Way itself is moving, falling toward the Andromeda Galaxy and the rest of the local group at roughly 250,000 miles per hour. And the entire local group is being pulled toward the Virgo cluster, and the Virgo cluster is itself being drawn toward a massive gravitational anomaly astronomers call the Great Attractor. Motion within motion within motion, all of it adding together into a total velocity relative to the cosmic microwave background. The afterglow of the Big Bang itself, of roughly 800,000 miles per hour. You, lying still, are travelling at 800,000 miles per hour through the universe. The crossing of the Milky Way is not something that awaits some future civilization with better engines. It is something that is already happening. We are just passengers, carried along by the gravity and momentum of a galaxy that has been travelling since before our sun was born. And this is the thought I want to leave with you tonight. Not the terrifying thoughts, though they are real, and they deserve to be held with honesty. Not the crushing timescales or the energy requirements, or the silence of the Fermi paradox, or the loneliness of the time-dilated traveller arriving at a galaxy 100,000 years removed from everything they ever loved. Those are true things, and sitting with them is part of what it means to look clearly at the universe we actually inhabit. But underneath all of those truths is another one, quieter and more sustaining. We are here, in a galaxy 100,000 light-years across, around a star 26,000 light-years from the centre, on a planet so small it vanishes into the background glow from the far shore of the Milky Way. We are here. We are the part of the universe that woke up. We are the matter and energy of the cosmos that somehow, through billions of years of stellar evolution and planetary formation and biological complexity, arranged itself into a configuration capable of asking the question, how long would it take to cross the galaxy we live in? The galaxy did not ask that question. The stars did not ask it. The black hole at the centre, with its 4 million solar masses of gravitational authority, does not ask it. We ask it. Small, temporary, fragile, extraordinary us. There is a phrase that has become something of a cliché in popular science, but clichés sometimes earn their place through the simple fact of being deeply, persistently true. We are the universe noticing itself. Carl Sagan said it in one form. Others have said it in others, but the version I keep returning to on nights like this one is slightly different. We are the universe asking itself where it ends. We are the cosmos measuring its own diameter, calculating its own crossing time, feeling the vertigo of its own scale through the medium of a temporary biological creature lying in a dark room on a small planet in an outer spiral arm of a galaxy it will probably never cross. There is something in that. Something that feels, to me, not small, but immense. Not humiliating, but humbling in the best sense. We are not diminished by the scale of the Milky Way. We are the scale of the Milky Way thinking about itself, and that is a thing worth being. Thank you for joining me tonight on this crossing. Thank you for staying with me through the numbers and the darkness and the silence, and the long, slow accumulation of scale that is the Milky Way held honestly in the mind. If this journey moved something in you, if it made the night sky feel heavier and more wondrous and more worth looking at, I hope you will take a moment to like this exploration, or subscribe so we can keep making these journeys together. The next time you step outside on a clear night and look up, and I hope you do it soon, find that faint pale smear of light stretching across the sky. That is the disk of the galaxy seen edge on from inside. That is 100,000 light years of stars and gas and dust and silence and mystery and ancient light, compressed by distance into something you can cover with your thumb. You're inside it. You're moving through it at 515,000 miles per hour, and somewhere on the far side, 100,000 light years away, our question echoes outward into the dark, still travelling, still looking for an answer. Sleep well tonight. Keep looking up at the stars. Good night.